right. Hello. Hi, everybody, and welcome to this presentation on Neo4j Foundations for Scale. And presenting will be me, Tobias, like Max said, and I'll presenting together with Hugo from the Neo4j clustering team. I'm in the Neo4j Cypher team. We'll be talking about two new developments in Neo4j 5 that we are excited about, namely composite databases and autonomous clusters. Before that, we'll introduce a little example scenario that we'll base the rest of the presentation on. After introducing these features, we'll run a demo where we showcase these things, and after that, we'll hopefully have time to squeeze in a few questions as well. Otherwise, we'll take them asynchronously in chat. Okay, let's jump into the example scenario that we'll be looking at. So we'll be imagining that we are a business that runs a social network, and the data model, in very simple terms, is going to consist of person nodes and post nodes. And we'll have two different kinds of relationships. We'll have the follows relationship between persons, and we have the posted relationships between person and posts. And the interesting thing about this is that we expect this data to grow, to become very large. And we expect the person's data set to grow, but we actually expect the posts part of the data to grow much, much faster, potentially unbounded if we're lucky. And so that's a very quick overview of the scenario that we're imagining in the background here. Now let's jump into the first of the tools that we use to tackle this scaling problem here, and that is composite databases. So composite databases are, as you might have guessed, composed of other databases, and they are actually composed of other sort of standard databases. So the composite database itself doesn't contain any data. And what they do let you do is they allow special Cypher queries that lets you query data across all of these constituent databases. And this is the evolution of something called Fabric that existed in Neo4j 4. So let's have a look at how you manage composite databases. So you administer them with Neo4j admin commands, just like normal databases. For example, the first command here, create composite database social, which creates one of these composite databases, and it will immediately exist on all members across your Neo4j cluster. And then what we do is we mount other databases as constituents into this composite by creating aliases inside of the namespace of the composite database. So these are two examples of that. We create an alias social.people for the people DB database. And just like other databases, we can start, stop, and drop composite databases. All right. Now let's jump back a little bit to the example scenario where we have this data model. And we're going to try to come up with some scheme of splitting this data up across multiple databases that lets us scale in the way we expect. And the thing we have come up with based on the expected growth rates of these things is that we'll split the data into two different categories. The first category is going to be our people category. It's going to contain all the person nodes and all of the follows relationships connecting them together. And this will be placed on a single database, people DB. And the other category of data will be the posts data containing the post nodes. And we'll host these across some number of separate databases. And to connect the post back to the person that posted it, we'll employ this thing that we call the proxy node pattern. So on these databases, in addition to the post nodes, we'll introduce these thin proxy nodes that represents the person that posted it. And we'll strip these nodes of all properties except for the ID, which will act as sort of our foreign key that we'll use to connect back. And so when we query this data set using our composite database, we'll use this ID as a foreign key to join back the original shape of our data. So let's look at how some of these queries might look. Here's a very simple one. It targets only a single constituent of this composite, namely the people part. And then it does a normal cipher pattern match on that constituent. A slightly more complex query is this one. This one also goes to only a single constituent, but it does so dynamically by using the ID of the person. And here we have a user-defined function which implements our sharding scheme. So it decides on what shard should posts from this person live. An even more complicated example is this one. This one uses the built-in functions graph.names and graph.byname to actually reach out to all shards in this example and do a match on each one of them. And then we do a global aggregation where we order by the size of the post and we limit by 1 to effectively get the longest post across all of our constituent graphs. And now, connecting all of these pieces together, we have an example of a query that first goes to the people section of this data. It does a cipher pattern match there. It returns the persons followed by some given person. And in the next part of the query, it reaches out to each graph in turn, each posts graph in turn, and actually grabs the posts made by that person. And this last query showcases, I think, really the power of composite databases, where we have both an example of data federation, where you have data with different schemas and you connect them together. And we also have data sharding, where we have sort of homogeneous data and we split it and separate it out into parts. And with that, let's switch over to Hugo.
Great, thanks, Tobias. Can everyone hear me? Yeah, cool. So I'm going to talk to you about the second of the two features that we mentioned up top. When I start talking to you about autonomous clusters, it may not be immediately obvious how they relate to composite databases, but just bear with me, and I promise I will tie them together at the end, and I will explain why they work so well together, we think. Next slide, please, Tobias. So if you're familiar with Neo4j clusters from any of the 4 series or before, you'll have been familiar with words like core and read replica. Servers in your cluster had to have specific roles that were static over time, and converting between those roles was very difficult. And growing the cluster was also quite difficult. And that was irritating administratively, and so now in Neo4j 5, all of the servers in your cluster are treated the same. There's no concept of core or read replica anymore. They're just servers waiting to host your databases. The other thing that you might have been familiar with from Neo4j 4 is that every database would exist everywhere. So if you had 100 databases and 5 servers in your cluster, all of those 5 servers would have all 100 of your databases. Right? That also doesn't exist in Neo4j 5 with autonomous clusters. So a database can have a number of copies that you specify, and those copies can be in one of 2 modes, primary or secondary. And those copies will be spread across some of the servers of your cluster by an automated component that I'll talk about shortly. On those 2 modes, primary copies of your database are responsible for maintaining the fault tolerance and the high availability of your data, and secondary copies of your databases are responsible for achieving scalability of read queries. Next slide, please, Tobias. All right, so you've got your fancy new Neo4j 5 autonomous cluster, and it's empty. There's nothing on it. How do you even use it? Well, you can run a Neo4j admin command like the one on the slide to create a database with a fixed number of copies, as I explained. And then a component called the database allocator will go away and pick servers for that database to be created on. Next slide, please. So in this example, we can see the allocator has picked servers 3, 4, 5, and 6 to host PeopleDB. One thing that is the same between Neo4j 4 and Neo4j 5 is that for PeopleDB, only one of those primaries will be responsible for accepting writes at any given time. But if the writing primary dies or is temporarily unavailable or overloaded, then another one of the primaries will automatically step in. So that behaves similarly to cores if you're used to Neo4j 4. Okay, that's fine, but you've got unused servers here, and you've only got one database. Most complex deployments, especially if you shard, will have many databases. So what happens if you create another one? So if you create a second database, in this example called PostsDB, and you ask for a number of copies of that, the database allocator will attempt to spread the databases out across your available servers, your available resources, as best it can. So you can see in this, you can see here that they mostly don't co-locate. And yeah, PostsDB exists on its servers, PeopleDB exists on its servers, and you have scaled out because each of those databases has access to the result, with the exception of server 6, has access to the resources of that entire machine. There are a couple of exceptions to this where databases exist on every machine in the cluster. One is the system database, which is an internal database we use to control clusters, and the other is the composite databases that Tobias mentioned that are virtual in a sense, so they exist everywhere. Next slide, please, Tobias. All right, fine. In some sense, what I've just presented might seem more complicated than what you had before. So what are you getting as a benefit, right? Well, for one thing, your clusters can get much, much bigger now than they ever could before. right? So remember what I said earlier about having all of the copies of your databases on all of your servers. That meant that if you wanted to have 10 servers, then you had 10 copies of every database, and you ran into some inherent scaling limits, right? So your clusters were of limited size. Now that's not true, because some of those databases, they're disjoint. They exist on only a subset of servers. So you can have far more servers within the same cluster with the same authentication, with the same procedures, et cetera, et cetera. So you can scale up, but you can also scale back down again, right? Very easily with Cypher commands. So you can adapt to a changing workload. So it's not just about what if your data grows over time and you need to have more servers. It's also about what if you have some temporary spike of work. Let's say you're Amazon and you've got Prime Day or Black Friday coming up, right? So the autonomous clusters in 5x are much more elastic than clusters have ever been before. Next slide, please. In addition to being able to grow and shrink the number of servers in your cluster, you can also grow and shrink the number of copies of a given database, right? So earlier we created PeopleDB and it had 3 primary copies and 1 secondary, but you can alter that at runtime. Next slide, please. Down to 2 primary copies and 1 secondary copy. And it's just a simple query. Next slide. Like this one here, right? That's all it takes. And the beauty of this, next slide, please, Tobias. The beauty of this really is that all of these moves, adding servers, moving databases across servers, they're all driven by you, the user. You write transactional commands to say what you want declaratively, but you don't have to actually control the moves. The cluster automatically migrates databases for you in the background, always maintaining fault tolerance, always maintaining high availability. So if you're one of these people that's been burned by maintaining stateful apps in an orchestrator in the past, none of those problems exist here, because we built this from the ground up to handle that situation. So databases are migrated only as fast as they can be across the database, across the cluster, in order to maintain those key invariants of high availability and fault tolerance. But also, this system is more flexible, right? So let's say that you had have some procedures that custom procedures that you've written that do GPU compute, right? Some crazy fancy new graph algorithm, but you only want to run that on one of your databases, and you only have one server which has GPUs in it. Well, previously, that was kind of annoying to do, because you had to have all of the databases on that secondary, so on that read replica server which had the GPUs in it. But now you can mix in a server with specialized hardware and have just the databases that you want move over to that server, where you can then run the algorithms, and you can maybe move those databases off again, all with simple Cypher commands, run safely at runtime, transparent to your end users. You can also have a situation where maybe you're running some kind of multi-tenant app and one of your databases is acting out, right? Somebody is doing something insane and it's impacting other users on the system. Well, now it's much easier for you to create a kind of jail where you add servers and you can migrate the problematic database to those added servers, and isolate them until you can resolve the issue. And then you can remove the servers and all of the databases will come back together again. Next slide. So, and you can see, before I pass back to Tobias for the demo, I hope, how this plays well with composite databases, because composite databases allow you to make use of having many, many databases, but what they didn't allow you to do was horizontally scale out easily, right? So you can use them to query large numbers of databases underneath, but combined with autonomous clusters, now you can use your composite database and scale out the resources, horizontally scale out the data underneath as it grows or as your compute demands grow. And the composite database just keeps working, right? And your users never notice a thing. So the two things combined make it much, much easier and much safer for you to achieve these kinds of horizontal scaling architectures. And with that, I'll pass back to Tobias to show you how.
Thank you very much. All right, let's switch to this console that looks to be working. Excellent. Okay, so what I have running here is a setup based on this example scenario. And what we have inside here are 10 separate databases for containing posts data and a single database containing people. And we also have the system database, of course. And this whole thing is running on a 5-member cluster in Neo4j inside of Docker Compose. And we can see here from this query that each server is hosting 7 or 8 databases in total. And what I wanted to show here is I'm going to copy paste some commands here. I want to show setting up one of these composite databases and mounting all of these constituents into it. So let's do that like that. And let's run a show databases again. See that we now have our social database, which is of type composite. And let's switch to that database, social, and let's just, as an example, run one of these queries, which is very similar to one of the queries that I showed on the slides earlier. It basically reaches out and gets sort of a few posts by everybody followed by each person. And yeah, the data is generated automatically, so it's not going to be very interesting. But at least it shows how this composite database is able to query across all of these constituent databases. And now, as we talked about in the scenario setup, we imagine that our databases have grown by quite a lot, and perhaps to the point where we risk running out of disk space on the servers themselves, or perhaps we're running out of CPU and memory on the servers. We realized that we're going to have to scale out, and I'm going to initiate that here by telling Docker Compose to add 2 new servers to this setup. And we're going to have to wait for them to start here. So what I've done here is I've physically added 2 new instances to the cluster, and I'll hand it back over to Hugo to talk about how to plug those into the cluster and use them. We can't hear you, Hugo.
Oh, my apologies.
There you go.
That's the perils of the double mute. So now that Tobias has created the physical servers, we want to add them to the cluster. And you can do that by enabling them. So if Tobias runs a show servers command, he should see that 2 servers show up as free, right? And if you then copy the name of one of the free servers and then run a command called enable server, passing in the name, you will set those servers from free to enabled. And this might seem like, oh, why didn't they just join automatically? But this was a deliberate design choice so that you, the cluster operator, you have to explicitly let these new servers in, right? So now you've let them in. Another thing to notice here is that they don't yet host any databases besides the system database and the composite database. So just enabling a server, for the cautious among you, does not actually move the databases. In order to move the databases, automatically spread them out, you need to run a command called reallocate databases. So now if we run show servers again, you should see that the number of databases is much more evenly balanced across the system. And that will take some time, because obviously these are actual databases being moved in the background. And remember, I said that the movement of them is handled by the system at precisely the pace the system can manage, whilst keeping these things highly available, like guaranteeing that they are remaining fault tolerant and highly available. But now we've reallocated the databases. We've spread the databases out, and we've probably got a bunch more headroom on our expensive SSDs or on our expensive CPUs. And if you run the same composite query that you ran earlier, you'll see you'll get the exact same result, right? And that would have been true if you'd run it like constantly whilst those databases had been reallocating in the background. That was never interrupted, right? So the result hasn't changed, but you've scaled out. All right. But earlier I mentioned that you don't just want to scale up. Sometimes you want to scale back down again, right? So how do you do that? How do you remove a server? So the first thing that you need to do is you need to deallocate the databases from the server that you want to remove. So if you pick a server and you so you run deallocate, then you run show servers again, you'll see that server is deallocating. And it will, the number of databases it hosts will steadily creep back down to 2 as those databases are spread out again back across the system. Now, they still have 2 because you are essentially, you're still hosting system and you still host the composite database. Once you've deallocated that server, once you've seen it get to a low enough number, then you can drop the server, right? And then that physically removes the server from the system. So if you run show servers yield, you can see that it only hosted 2 databases at the end, and it's now been dropped. So you've scaled the system down. It's still showing up because the server's still on, but once a dropped server is turned off, like, it actually leaves the system, if that makes sense. And your data is already safe and respecting its constraints spread back out across the system. And if you run that composite query one final time, you'll see again that the result is the same. In some sense, it's exciting and boring, right? It's the same result, but that's what we wanted, because what you want your distributed systems to be is boring, I promise you. So yeah, that's how those 2 things play nicely together. And Tobias, if you want to jump back to the slides, we'll do some wrap up. By the way, we'll distribute the slides afterwards, and there is source available for running the demo yourself and some extra commands that you need to run for setup. But we had to skip some of the setup for time. Okay, so we're just about at the end here. Hopefully, you're convinced that these 2 features combined can give you value. Right? If you have a terabyte of posts data when you first enter the system and you sharded them 10 ways or 20 ways or whatever, right? You can grow to tens and tens or hundreds of terabytes of posts, right? With this system, all transparent to your users. Next slide, please, Tobias. We know that it's not a complete scaling picture. We believe that it addresses the vast majority of the scaling problems that our users today face, but there are still some things that we'd like to tackle in future. So for one thing, the sharding scheme is not transparent. You haven't got that amazing thing where you get to pretend that there's only one graph, right? We'd love to do that eventually. And any given transaction may target multiple of the shards in a composite database, but it can only write to one of them. And that restriction still exists, though, again, we'd like to solve it. So for us, what these 2 features do is they lay a foundation for you guys to go out and solve your scaling problems with confidence, and for us to solve the remaining problems, closing that last 1-2% gap to a full and complete surface. In the near term, next slide, please. There's just a couple of things that are coming up in a sort of hopefully early 5x release. So you may be wondering how you control which servers in a cluster host which databases. There are controls. You can tell a server that it can or can't host certain databases by name, and you can also tell a server that it can only host databases in secondary mode or that it can only host databases in primary mode. But that isn't necessarily as rich a surface as customers or users may want in order to control, where their given database is within a much larger cluster. So we're planning to add support for definitions like this that will be automatically respected as you alter your cluster or database over time, and they can achieve like a geographic layout, so demonstrated on the next slide. And so you would write that topology once, and as you added and removed servers, the system would put you in guide rails so that those constraints are always respected, and we automatically move the databases around to ensure that. And that's it. We might have 2 or 3 minutes left for questions if we've been fast enough. I hope you enjoyed it. So
All right. Thank you guys for a very well organized talk. So autonomous clusters is a really interesting topic. So let's see if we have some questions here from the audience. I know that I saw something before. All right. So can primary and secondary also be set on server level, so that certain databases can only be secondary on server 1 and the other base is primary on server 1?
So the way that it works is you can set a constraint on server level. By default, a server can host any database in any mode if you don't constrain it. So it can host it can host people in primary mode and posts in secondary mode if you've chosen to create secondaries for those. But what you can do is you can say, okay, I want this server to only host secondaries or this server to only host primaries. And what happens then is that information is given as is collected by the allocator, and so the allocator will only put secondary copies of a given database on a server that can only host secondaries. Now, what that means is if you say this server can only host secondaries, and then you never create any secondaries, that server will always be empty. So that's like a side effect of that. But you can very much say this server is for secondaries only.
Okay, all right. So for example, if you have a cluster where you might do some heavy workloads on your secondaries, you don't want to put like a primary on that system as well.
Exactly.
Oh, that's amazing. Okay, so I think we have another question here from Simon. And would autonomous clusters be useful for keeping a tenant's data separate with respect to other tenants?
Absolutely. So you'd have to write some kind of light config layer on top, especially because we don't yet have those richer constraints that I showed in the last slide. Those are coming soon. The only thing we support are the constraining a server to a given mode and giving a server a list of allowed databases or a list of denied databases. But you can still use that to enforce tenant separation, no problem, right? You can configure those servers to do that. And you can do that at runtime, I should clarify, right? So you can update the databases that a server is not allowed to host, like at runtime. You don't have to turn the server off to do that.
All right, so you can configure like specific access controls for one database and put your constraints for a specific database and not just the whole cluster?
Yes, if I'm understanding the clarification correctly. But so you could very much say I've got these three. You could federate completely, right? So you could have 6 servers, and you could have 3 servers that are allowed to host foo, or and deny bar, and then 3 other servers that allow bar and deny foo, and that will force them to be separated.
Wow. Wow, that's sounds like a very good way to run very, very large clusters, for sure. All right. Do we have any more questions from the audience? There's a lot of claps here, at least. It seems to be enjoying this talk. So I would like to thank you guys very much. Oh, now we have another question here that popped up. So for writes, still, will it use only one primary database server? Then how would you spread the CPU load?
Okay, so there's a sort of couple of elements to that question, and I'll wait at the end, so I'll try and answer it quickly. The one is that all queries, whether writes or reads, will consume CPU load. So you can always spread databases out, and that will reduce the CPU load on that given server. So if a server is the writing primary for foo, but it's also a secondary for bar and baz, you can alter your system so that bar and baz and their incumbent queries go elsewhere to relieve the pressure on that primary writer for foo. But underneath as well, each server is attempting to be the writing primary for only a small number of databases. So that the ability to write is also balanced across servers evenly.
All right. So how do you, now this is a question for me then. So for example, when you're working with these clusters, will you have to specify in your driver which kind of node you wanna query, or do you just send out the query to the cluster and it will do the routing for you?
So you can specify in your driver what database you want to talk to, and then the driver and the cluster collaborate to just make that work transparently to you. So if you hit a server that doesn't host the database you asked for, the query will be proxied for you in the background, and you won't know. But also the driver will get a routing table that will tell it, well, actually that database isn't here, so it's more efficient if you go over there. And specifically, if you're asking for composite databases, that's how they work as well, right? So, if you send a query to a composite database, it goes to one of the servers, and then that sends out those proxies, those queries in the backgrounds to other servers that might host those databases within the composite.
All right. And last question. You were talking about composite databases, and you were talking about autonomous clusters, right? And will they be used often in conjunction or just separately?
Our hope is that you can use them in conjunction, right? Because that's like the core thesis is that the power of composite databases has always been really cool, but it's been hard to operate, large fabric databases historically. So composite brings that power into the system and makes it easier to control, and also makes it so that you can get that horizontal scaling within a single cluster. Right, much more easily.
Perfect. Thank you, guys. I'm gonna stop this here, and we'll have our next speakers up on stage in a minute or so. Thank you, Tobias. Thank you, Hugo. Have a good day.
Thanks very much, guys.